Hello everyone, welcome back to my YouTube channel. Till now, we have seen every single intuition behind Perceptron. We have seen the geometrical intuition as well as we have seen how the weights are updated in Perceptron. So now it's time to build Perceptron algorithm from scratch. So let's start. Here, first thing I'm going to do is to import the two important libraries, that is NumPy and Pandas. Let's make the alias of NumPy as NP and the alias of Pandas as PD. Now I'm going to read the CSV file. Here I have taken the same dataset which I have shown you as an example in the previous videos. Let's store this climate2 dataset in the variable df and let's try to print it. As you are already familiar with this dataset contains two features, that is temperature and humidity. Based on these two features, we are going to have a label, that is whether the climate is tropical or it is balanced. So in all, there are two classes and we have to use this perceptron algorithm to make the decision boundary between these two classes, and we have to predict whether the climate will be tropical or it will be balanced based on these two features that will be provided as a test data. So now you can see in this particular data set, our classes are in the form of text, that is tropical and balanced. So we are going to convert it into numerical values, that is 1 and 0. So for that I am going to use label encoder. In the dataset, you can see we have to convert this label column. So this label column can be accessed with the help of the variable df, because this label column is consisted in this particular df. So df of label will be equal to, now we are going to convert the values tropical and balanced inside this particular column label. So for that we are going to call the function fit transform, and in that particular function we are going to put the argument, that is df of label, that is the column itself. And through this you can see, if we print the dataset again, in the label column you can see the tropical is now converted into 1 and all the balanced values are now converted into zeros. So that is why we have used label encoder. So now our dataset is ready. But here you can see that features as well as the label is into a single dataset. But we don't want that. We'll have to separate the features and labels, because features are going to be used as an input to the algorithm and labels are going to be used to check whether the output from this input features is correct or not. Basically we are going to use the label to find out errors. So for that we have to separate the features and labels. So you can see that in the dataset we have the features in the first two columns, that means the columns at index 0 as well as 1. So you can access these two columns with the help of the iloc functionality, and since we want all the rows we will give a colon, and after that through slicing concept, since we require only the first two index columns, so we will write colon 2. That means the column that is present on index 1 as well as 2 will only be fed into the variable x. And now in the variable y we want only the column label. The label column can be accessed again through this concept of slicing. We want all the rows, that is why we have used colon, and since we want only the column that is present on index 2, that is the label column, so we'll write 2 inside it. And you can see in the y variable we have now stored the label column. So you can see here we have separated the features from labels. Features are stored in x variable and labels are stored in y variable. Now we are going to build the perceptron algorithm in such a manner that it will accept array for features as well as for label also it will require array as the data type. So now we have converted the feature as well as the labels into an array data type with the help of np.array function. So this is how we have converted the data frames into arrays. And I think now we are set for building the perceptron algorithm, because we already have separated the features from labels. So for building the perceptron algorithm I am going to use class based functionality. as we are going to have multiple functions inside it, that is why class-based approach would be good. So here I have defined a class named Perceptron. Now if you remember, in the previous video we have already framed the entire algorithm for Perceptron. Based on that algorithm only I am going to write the functionalities in this particular code. So here first there has to be a function called as train. Here the entire training logic will be present. Next we will have the predict function. In this particular functionality we are going to find out the weighted sum with the help of the finalized weights, and this function can also be used to test on unseen dataset. And then finally we'll be having the activation function over here, in which it will do the same thing what activation function does. Here we are going to define the logic of step function. So now first we'll have to initialize all the variables which will be required in this particular algorithm. So for that we'll be using the init method. In this we'll be defining all the variables that will be used throughout the class. So let's write the parameter self. Next, what we require. The most important thing that we require is the input size. That means how many features are present in the dataset. For example, in our dataset, in the x variable we have the temperature as well as the humidity columns, which means that there are two features, which says that the input size is 2. Next we require the learning rate parameter. So here I have already told you what is the significance of learning rate in the previous video. Learning rate will control the model convergence. We will have to set the optimal value of learning rate, which ranges from 0.1 to 0.0001. Here we have defined the learning rate value as 0.01. We then will require the number of epochs. I already have told you what is the significance of epochs. Here epochs are nothing but iterations, the number of iterations which we are going to follow for this particular perceptron algorithm. Here I have defined 1000 as the number of epochs. So let me quickly declare these variables so that we can access it throughout the class. So you can see that we have declared all the variables. Now with these three variables we'll also require one more most important variable, which will be the weights. These weights play a very important role in finding out the prediction. Now we have seen the significance of weights. Basically, weights defines the importance of a particular feature. The more is the weight, the more is the importance of that particular feature. Initially, we do not know what exactly is the importance of any feature. We don't know whether temperature is important or humidity is more important. That is why initially we will initialize the weights as a random value, which will be same for all the features. So here I am going to define 1 as the value for all the weights. In NumPy, we have a function called as ones, which will create an array of specified size with all the values as 1. Every feature will have its weight. That means it is dependent on the input size. But we will have to write +1 to this input size, because we already know that there is an additional term called as bias weight, whose feature is a virtual input and its value is always initiated as 1. So that is why whatever is the input size, in addition to that we'll have to add 1, because there is a bias weight also which is associated with it. So here we are going to write np.ones, and in this particular ones function we will write the input size. As you know, the input size contains the total number of features and we'll add 1 to it. This 1 will be for the bias weight term. So even if you have hundreds of features in the dataset, you don't have to specify separately that your dataset contains 100 features and 1 has to be added to it. This will automatically create an array of all the values ones. I hope now all the important variables which will be required throughout the class are declared. So now let's move on to the first function, that is train function. This is the main part, and this function will be the entry point to the input dataset. So here, as you know, training will be done for the features as well as the labels will be used for checking whether the features are predicting it correct or not. That is why we will require two things as the parameters in this function. Let's put the features that are stored in the variable x in this particular variable called as training data, and we will declare a new variable called as label, and into this we will write the label which is stored in the variable y. So these two variables will be passed into the Perceptron train function. So let's quickly declare it. So here I have declared a variable in which I'll be storing the Perceptron class, and here Perceptron class will require the input size because it will be dynamic. So here we'll specify the input size separately, and let's say for now the input size is 2 because in our dataset the number of features are 2. Now after this we will call the train function inside the Perceptron, which is stored in this particular variable Perceptron, Perceptron.train. Then inside this function we have to pass these two parameters, that is the training data as well as the label. So let's write it. Similarly, in the function definition also we will declare these two variables, that is the training data and the label. These two variables will be used in the function train. So now let's try to build the logic. If you remember, in the previous video we have seen the algorithm, and in that it was specified that the Perceptron algorithm will try to train all its data points for specified number of epochs. So that is why we are going to use a for loop for epoch in range. Inside this we'll pass the variable self.epochs because we have already defined that the number of epochs will be 1000. Now into this for loop we will again declare one more for loop, and this for loop is going to iterate over all the inputs and labels which are present inside our dataset. We will iterate over the training data as well as the label variable at once with the help of the zip function. So inside this zip function we'll mention these parameters training data and label. So you can see corresponding to the training data we have the inputs variable, and if you remember in the training data we had the x terms, that is the features. So first time for the loop the inputs variable will contain the first record without label, that means only the features will be present, and in the label variable the y part of that feature record, that means the output, will be present. Now here for each data point we have to find out the prediction of it with the help of the algorithm that we are defining. That is why we have declared a variable prediction, and this prediction variable will store the returned value of the function predict which we have defined in the class. We haven't written the logic yet. We'll write the logic now for the predict part. Basically this predict function will take the inputs, that means only the features which are present for every single data point. As you know, features are responsible for making out the predictions. Now for making the prediction, what exactly we require? First we have to find out the weighted sum of all the feature inputs, that means we will require the weights as well as the inputs because the formula contains summation of xi multiplied by wi. So basically we are requiring the weights as well as the inputs. Inputs we already have in this particular function because this function has an argument called as input which will be taken from the function train. But if you carefully observe, here we have defined the input size as 2 because we had two features x1 and x2, but in the formula we also have x0, that is nothing but the virtual input, and its value will always be initiated to 1 and it will always remain constant. Since x0 is not present in the variable inputs, so that is why we'll have to explicitly insert the x0 value in the array that is given to you. And since there is only one value that is to be inserted, we have a functionality in NumPy which is called as insert, which takes three arguments. The first is the array in which you have to insert the element. The second argument takes the index, that is the position at which you have to put the element, and the third argument takes what exactly you need to put. That means the value that you need to insert. So here let's say we have an array of 1 and 2 and we have stored it in the variable I. So if we want to insert the value 1 at index 0, so we can write it in such manner: np.insert I, 0, 1. So here the value 1 will be inserted at the location 0. Let's execute this cell and see the results. So here you can see at index 0 the value 1 is inserted. Now we are going to write the same thing here, np.insert, since we have the input variable in which it contains the array, we'll write it as inputs, and in it we have to insert the value 1 at index 0, which is nothing but the virtual input, that is x0. And we will store the final array in the variable input with bias. So now we are ready with the input features. Now we have to calculate the weighted sum, and for calculating the weighted sum we have a functionality in NumPy which is dot function. Basically we have to calculate the dot product of the two vectors, that is the feature inputs, that is x, and the weights that are associated with it, and will store the dot product in the variable weighted sum. We have to write np dot dot. In this particular function we have to define the two parameters for which we have to calculate the dot product. First is the input with bias, which contains the x0 term also, and next we have to write self dot weights variables, which contains the weights which we have initialized. This dot function will compute the dot product, that means the weighted sum, and it will store it in the variable weighted sum. Now once we calculate the weighted sum, if you remember, the next step was to calculate the activation function value of that weighted sum. So for that we will now have to move on to the activation function which we have to define now. So let's return it first. We'll return this weighted sum value as a parameter to the activation function by calling it in the return statement. Now this will take the control to the activation function. Now here we have to define the simple logic for the step function. Let's first write the weighted sum as a parameter to this declaration of activation function. Now in this particular activation function the logic is very simple. If the weighted sum value is greater than or equal to 0, then we'll have to return the value 1. Otherwise, if the weighted sum value is less than 0, in that case we'll have to return 0 as the value. So this is what is the simple logic of activation function is. Now this activation function returned value, where it will be stored. If you remember, we came to the predict function. From that predict function we came to the activation function, but where that predict function was called, it was called in the train function, and the returned value of the activation function will be stored in the variable prediction. So you can see, for every single record we are going to find out the prediction using the weights that are present in the current state, and the predicted value of the current feature will be stored in the variable prediction. And now that we have predicted, now is the time to check whether the prediction is correct or not. So for checking that, we will have to define the error term. If you remember, the error is calculated with the help of the formula, that is the actual output minus the predicted output. As we already know, the actual output is stored in the variable label as we are iterating over every single record. So for each record, the actual output will be stored in the variable label. So we'll write label minus prediction. So here label minus prediction will be the error, and which will be stored in the variable error. This will be done for each and every record. And now it's not always possible that the model will always converge only after doing 1000 epochs. The model may converge in first 6 to 7 epochs also. So for that we'll have to find out where the model will be able to converge, and for that we'll declare a variable total error. The total error value is initiated to 0. After a particular iteration, if the total error that is calculated is 0, that means if the sum of error of all the data points is coming out to be 0, that means the model has converged. And if the model has converged early, then we can stop the iteration and we can return the final weights and the prediction. That is why we have initialized this variable total error, which will contain the sum of all the errors that are present for each and every data points. And after every single iteration, we will check whether the total error equals 0. If it is 0, then we will straight away print that the model has converged in these many epochs. Now I have added 1 to the epochs variable because our iteration starts from 0. That is why we have to add 1 to it. And after this, we can write the return statement that we have got this particular final weights for the dataset that is provided. So now I hope that what is the significance of this term total error is clear to you all. It is just to find out whether the model has converged or not. If the total error is not 0, then the next iteration will occur. Now let's say for the current record in this particular iteration, if the prediction is not correct as per the actual output, then in that case there is a misclassification, and for avoiding this misclassification we will have to update the weights. You can see that we have the weights in such a manner W0, W1, W2 till Wn. You can say that the weights from W1 to Wn are the weights that are associated with the input features that is present in the dataset. But the weight W0 is not the weight associated with the input feature, it is the bias weight that is present, which is associated with the virtual input whose value is always initiated to 1. So therefore, in the weights array also, we will update the weights other than W0 through a separate formula and the weight for W0 through a different formula. So this formula that I am writing now will be for the weights that will not contain W0. Apart from W0, all the weights can use this formula. So that is why I have written self.weights, and then using the slicing concept I have avoided the weight W0 that is present in the index 0. And in this old weight we are going to add the new weight. If you remember the formula, it was learning rate multiplied by y minus y hat, which is the actual minus the predicted output multiplied by the feature input. Here learning rate is present in the variable self.learning rate multiplied by error. Now why error? Because in the error declaration you can see that we have written label minus prediction, which is the actual output minus the predicted output, and multiplied by the inputs variable, because this inputs variable contains the current records input feature. And you can see through this particular formula we will be able to update the weights starting from W1 till Wn. But now what about W0? Again we have to write the separate formula for it. So this will be dedicated to the weight that is associated at the index 0. So self.weights, we will define the position 0 and the formula will remain the same. Only the part is that instead of inputs we are not going to write anything, because here the input is x0 and x0 value is always 1. So instead of writing 1, we'll not write it, as multiplication of any term with 1 is that term itself. So this is how the formula is framed. So you can now see we are done building the entire logic for training the perceptron with the data that is going to be provided to it. I think we are missing something. What if a case arises that even after training for 1000 epochs, that means even after training for the specified number of epochs, our model has not converged, then in that case we can have a print statement that states that the training is completed but the model has not got converged. So now we are done with the full code. Let's try to execute this particular cell. Let's make sure that we have called the function train. And after executing this cell, we are getting an error. The error says that numpy object is not iterable, and the error is on line number 11. So let's move to line number 11 and see what exactly is that error. So if you carefully observe over here, you can see the variable label is acting as a temporary variable in the for loop, and the same variable is given to the zip function. This variable is actually creating the chaos. So let's just write labels instead of label, and this labels was taken from the input data. So let's change the name of that label variable there also. So here you can see, here also we'll have to add an s to the variable label. So it will be labels, and here also we'll write labels. Now we have changed the variable name, and I hope now this will properly execute. So let's execute the cell again, and here you can see we have got the output, and the output says that the model has got converged after 11 epochs, and these are the final weights. 0.93 is the bias weight, and the rest are the weights that are associated with the input features. If you remember, we have initialized these weights as 1, and now after proper training of the perceptron algorithm for this particular dataset, the weights have now changed to this particular weights, and through these weights now we can easily predict the climate, whether it will be tropical or balanced for any unseen data, which has two features, temperature and humidity. So let's try to test our perceptron algorithm onto that data. So here you can see, for testing I have defined a variable called as test data, and in this I am going to define an array. This array will contain simple 2-3 features for which we are going to find out the prediction. So let's try to add the unseen data, which will be close to this input data set, because here we already have the label for it, and for any random unseen data we do not have the actual output for it, so we won't be able to check whether the perceptron algorithm is correctly working or not. So let's try to write the first unseen record whose values will be close to these values. So the value that is closest to 29.5 I am writing here. So let's take 30.2 as the temperature, and let's take the humidity value as 63.2. This is the first record. The output for this must be 1 because it belongs to the tropical class. Similarly, let's try to take one more record whose output will be balanced. That means its output will be 0 because it belongs to the balanced class. So let's take some unseen value. So here you can see I have added these two test data records. Now one by one we'll have to iterate over it, and we'll have to find out the prediction for it. So let's use a for loop for data in test data. This data is a temporary variable which will contain each and every record one by one. So in this particular for loop we'll call the predict function inside the perceptron class, because in the predict function we are going to find out the dot product of the weights as well as the input features, and once it calculates the dot product of the finalized weights and the input feature values, it will call the activation function and will calculate the final prediction. So that is why we are calling the predict function, and into this predict function we are going to pass the data variable, which is nothing but the first record for now and the last record for the next iteration. And let's try to store this particular prediction value in the variable prediction, and then we will print the value that is associated in this particular prediction variable, which will be the prediction for the input unseen data. So now we are all set to execute this particular cell. So let's try to execute this cell, and you can see it has got executed successfully, and you can see we have got the output, that is the prediction associated with every single data point that we have put as the test data, and whatever we expected that the output of the first data point must be 1 and the output of the second data point must be 0, we have got the same results. That means our perceptron is working totally fine. Similarly, we can have two more data points, or we can have any number of data points, that is the data which was not used for training the perceptron, and we can test it. So let's try it for some new values. Now let's execute the cell again, and you can see we have got the prediction, and the prediction is as expected. It's correct. Similarly, you can give any input data to this particular perceptron algorithm to train, and you just have to write the specified number of input size. You can have any number of features in your dataset, and this perceptron class will successfully train that input data. In this particular code, we have put all the concepts that we have learned in the previous videos related to perceptron. I'm sure that the entire code must be crystal clear to all of you. If you guys have any single doubts, then you can put it in the comment section. If you guys have any reviews or suggestions related to this particular video or for the upcoming videos, then also you can put it in the comment section. Please share this particular video with all your friends because they will also get benefit out of this. And if you like this video, please like, share and subscribe to my channel. Also hit the bell icon and don't forget to follow me on Instagram. Also join me on Telegram. Link is in the description box. Have a nice day.